In this video, we're going to go over some of the basic rules of probability. A branch of mathematics called the probability calculus is the basics of statistical reasoning. It provides rules for calculating unknown probabilities when some probabilities are known. If we know, for example, that the probability of obtaining a head on a single toss of a fair coin is 1/2, then we can use the mathematical theory of probability to calculate the probability of obtaining all heads on 2, 3, or more tosses of a fair coin. In this video, we're going to go over some of the basic rules of the probability calculus. But before we get to those rules, we need to go over some preliminaries. First, before examining the mathematical rules of the probability calculus, we should note that any assignment of a probability value is based on general background information, or on evidence regarding specific conditions, even if this background information or specific conditions aren't always made explicit. In other words, probability assignments are always conditional on the assumed truth of such information. So for example, what's the odds of drawing a heart conditional on this being a standard deck? Thus, the probability of a coin toss results in heads being equal to 1/2, it's conditional on the coin having the usual design and being balanced in the usual fair way. Similarly, the probability that your grandmother will attend a Lady Gaga concert this weekend is conditional on no one's offering her some large amount of money to go. Presumably, the odds that grandma's going to go see Lady Gaga, pretty low, conditional on the normal state of affairs, but if it was conditional on the state of affairs where she was being offered lots of money to go, well, maybe that would make a difference. Statements of probability values are usually written in this form, which we can read as the probability of a statement H on evidence E is equal to N. So what we've got here, when you see this, it's a probability claim. This indicates that. And it's the probability of what? It's a probability of this claim H conditional on this evidence E. So it's a claim of how probable is this given this, and that's going to be equal to N. Sometimes, however, when it is clearly understood that a probability value is conditional on general background information, very general background information, and not on any special evidence, we just write the probability of H and then equal to N, omitting any reference to evidence. That's not the typical practice. That's not what it's not what we're going to do often, but we'll see it every now and then, so worth pointing out. Okay, the first rule of the probability calculus: the value N in a sentence of the form, the probability of H given E is equal to N, must be a single real digit between 0 and 1 inclusive, meaning that 0 and 1 can be used. This rule expresses a convention of using 0 and 1 as lower and upper limits of probability values and of assigning a unique probability value to any sentence in a given context. 0 is used for something that has no probability of happening, no chance of happening, and 1 is used to indicate that which is guaranteed or certain to happen. Because of this rule, assignment probabilities like 0.25, 5/8, or 0.9999 are all acceptable. Assigning probabilities like -1 or 1.23 are not, because they're not real numbers that fall in between 0 and 1. If H follows deductively from E, according to our second rule, then the probability of H given E equals 1. This is because 1 applies to anything that's certain to happen. To say that H follows deductively from E means that if E is true, then H must be true also. If this is so, then the probability of H on evidence E takes the highest possible value, that is 1. Let's look at some examples of this second rule. So, the probability that a black or a red card is drawn, given that a card is drawn from a standard deck, is going to be 1. That's because every single card in a standard deck is either red or black. So if you're pulling a card from a standard deck, there's no way it could be anything other than black or red. The probability that Mrs. Jones is married, given that Mrs. Jones has a spouse, that's going to be 1. there's no way she can be married and not have a spouse. If she has a spouse, then she's married. So it's 1. Note, however, that there are multiple ways in which the claim that Mrs. Jones is married can be won. If we had said Mrs. Jones is married if Mrs. Jones has a husband, that would also be a way for the probability to be won. This doesn't exhaust all the ways that Mrs. Jones can be married, but it's sufficient that if it's true, then this has to be true. Same with Mrs. Jones has a wife. Okay, let's look at an example or two of the opposite phenomenon, when you've got a 0 in for the probability. Take this one. 5 aces are drawn. Given that 5 cards are drawn from a standard deck without replacing in the deck the cards after they're drawn. Well, a standard deck only has 4 aces, and if the cards aren't being replaced, no card can be drawn twice, so it's impossible, if 5 cards are drawn from a standard deck without replacing the cards, that all 5 can be aces. So that's why this is 0. Similarly, the claim that Mrs. Jones is married is 0 if it's on the evidence that Mrs. Jones is single. That is, if she doesn't have a spouse or significant other. If you're not with anybody, you can't be married. Rule number 3. If 2 sentences, H1 and H2, are mutually exclusive, that is, if they can't both be true at the same time, then on the same evidence in both cases, the probability that either H1 or H2 is true is equal to the sum of their individual probabilities. This can be expressed symbolically as the probability of H1 or H2 given E is equal to the probability of H1 given E plus the probability of H2 given E. This type of probability is disjunctive. A disjunction, and this is important, is a compound sentence with or an equivalent connective, such as unless, and its major connective. Examples include the coin came up heads, or the coin came up tails, and the coin came up heads unless it came up tails. So what's important about the disjunction is it's going to be one or the other, but not both things. Because if it wasn't that type of situation, this formula wouldn't work appropriately. So it's got to be a case of a disjunction where it's one out of a set of things, but not both or all. The rule we had was stated for 2 mutually exclusive sentences, but it can be generalized to any number of mutually exclusive sentences. So take this example. The probability of H1 or H2 or H3 given E, if they're all mutually exclusive, that is, if only one of them can be true at most at a time, then it's equal to the probability of H1 given E plus the probability of H2 given E and the probability of H3 given E. It allows us to calculate the unknown probability of a disjunction when each disjunct is incompatible with all the other possibilities and when all the individual disjuncts are known. Okay, so let's take a look at an example of how you'd use 3 to figure out a probability. So if you were asked to calculate the probability that a fair standard die lands on a 5 or 6. So what are you trying to figure out? The probability that the die will land on a 5 or the probability that the die will land on a 6, given that the die is fair and standard. This is equal to the probability that a die will land on a 5, given that the die is fair and standard, plus the probability that the die will land on a 6, and the die is fair and standard. So, given that the probability that a die will land on a 5, if it's fair and standard, that is 6-sided, with numbers 1 through 6, that's going to be 1/6. The odds that the die will land on a 6, if the die is fair and standard, also 1/6. So you add 1/6 together plus 1/6, you get 2/6, which reduced to 1/3. So the answer to the probability that a die will land on a 5 or 6, given that the die is fair and standard, is 1/3. And of course, we can see that that's right. Rule 4 deals with the probabilities of conjunctions. A conjunction is a compound sentence with its major components connected by and or some other expression like moreover and a semicolon. Conjunctions indicate that the sentence as a whole is true just in case all of its components are true. Thus, the conjunction, there is a cat in the kitchen and a dog in the living room, is true if and only if there is both a cat in the kitchen and a dog in a living room. So this is the difference between a conjunction and a disjunction. A disjunction would say there is a cat in the kitchen or a dog in the living room. And if either there's a cat in the kitchen or a dog in the living room, then that disjunction is true. But in the case of a conjunction, you need both of the things to obtain in order for the conjunction to be true. Okay, so here's the fourth rule. The probability of the conjunction of two sentences is equal to the probability of the first sentence multiplied by the probability of the second sentence on the condition that the first sentence is true. This rule can be expressed symbolically as the probability of H1 and H2 given E equal to the probability of H1 given E times the probability of H2 over E and H1. So if in our cat and dog scenario, H1 was there's a cat in the kitchen, and H2 was that there's a dog in the living room, and our evidence was background knowledge like, we have a cat and a dog, both pets are home, things like this, you take the probability that the cat is in the kitchen, given your evidence, times the probability that the dog is in the living room, given the probability that, given your background evidence, and that the cat is in the kitchen. Why do we do this last part here? Well, the reason we do that is sometimes whether or not the first conjunct obtains affects whether or not the second conjunct obtains. Let's say, for example, that the cat and dog are never in the same room at the same time. That's going to influence the odds that the dog is in the living room. If the cat were in the living room, then the dog wouldn't be. But if the cat's in the kitchen, then the dog might be. And because this impacts the probability, that's why we have to conditionalize this second one on this first piece of information. Another way of stating the rule is to say that the probability that a conjunction is true is equal to the product of the probability of the first conjunct and probability that the second conjunct is true if the first one is true. Like Rule 3, Rule 4 can be generalized to any number of cases, but for simplicity here, we state it to cover only two conjuncts. When more than two conjuncts are involved, calculations become more complicated because the probability of each successive conjunct is conditional on the truth of all the preceding conjuncts. So, for example, the probability that H1 and H2 and H3 are true given E is equal to the probability that H1 is true given E times the probability that H2 is true given H1 and E, and that's times the probability that H3 is true given H1 and H2 and E. Okay, so let's look at an example of the application of Rule 4. So if you want to calculate the probability that a fair coin tossed twice will land on heads both times, you're going to want to use the fourth rule. You take the probability of H1 given E, and our evidence is that the coin is fair, so the probability that it'll land on heads is 1/2, and then you're going to multiply that by the probability that the second toss will be heads given that the first toss was heads, and the background evidence we've got. Of course, whether or not the first toss is heads is irrelevant to whether or not the second one will be heads. So this piece of information won't actually change the outcome at all. This is also going to be 1/2. So you've got a 1 out of 2 chance the first time multiplied by a 1 out of 2 chance the second time, and that gives us a fourth. And if you stop and think about it, you can see, yeah, that's right. There's 4 distinct possibilities equally likely to happen when you toss a fair coin twice. One is that heads shows up twice. One's a heads followed by tail combo, one's a tails followed by heads combo, and the other one's the tails shows up twice. And we were looking at the probability that heads will come up both times. And there's a 1 in 4 chance that that's what will happen, and that's what our answer says. Let's look at another example. So calculate the probability that an ace will be drawn from a standard deck twice in a row if the first card is not replaced. Okay, so here we've got H1 is pulling an ace on the first draw. H2 is pulling an ace on the second draw. To figure this out, we take the probability of drawing an ace the first time, given our evidence that it's a standard deck, so it's got 52 cards, in which 4 are aces, times the probability that the second one we pull is an ace. Now we've got our evidence about what a standard deck contains, but also the evidence, we're saying, look, one card's been picked already, and that card's an ace. So instead of it being 52 cards you're picking from, it's going to be 51, and only 3 of them are going to be aces. So with that in mind, we can see that, okay, at the start we had a 4 out of 52, which reduces to 1 out of 13 chance of drawing an ace. But after we've already pulled an ace, that number drops to 3 out of 51 for the second pull. And then we multiply these two together. It turns out to be 1 in 221 chance. Alright, last thing we're going to cover, in addition to the 4 rules, is this theorem. If the probability of H given E equals N, then the probability of not H given E is equal to 1 minus N. Here, not H is the negation or denial of the sentence H. For example, H could be a card drawn from a standard deck is red. Then not H is a card drawn from a standard deck is not red. Because the two sentences are mutually exclusive and jointly exhaustive, the truth of one and the false of the other exhaust all the possibilities, then the sum of probabilities of H and not H is equal to 1. Let's look at an example. If H stands for the probability of drawing an ace from a standard deck when a card is drawn blindly, then not H stands for the probability of drawing a card other than an ace from a standard deck when a card is drawn blindly. The probability of H is 4 to 52, which reduces to 1 out of 13. Thus, to figure out the probability of not H, one thing we can do is take 1, subtract the possibility that it's H, and then that gives us not H, which is 12 out of 13, the probability of drawing something other than an ace. If you look through a deck of cards, you'll realize, yep, that's the right number. Alright, so high five for learning the basic rules of the probability calculus. And the rest of this chapter we'll be going ahead and making some applications for these rules that you've just learned.